A single stone can weigh more than 50 elephants. Ancient civilizations moved millions of them. We often marvel at the final, silent monuments, but the true story is hidden in the journey. This is an investigation into the forgotten world of ancient logistics, the vast and intricate systems of planning, labor, and transport that supplied stone for history's greatest structures. By the end, you will understand the invisible architecture that made the pyramids and Stonehenge possible, a network more complex than the buildings themselves. We will uncover how quarries hundreds of miles away fed construction sites, and how societies without modern machinery coordinated thousands of people in a silent, monumental ballet. What does it truly mean to move a mountain, one stone at a time? The numbers alone are enough to silence any argument. For the Great Pyramid at Giza, the most studied megaproject in history, the builders required somewhere between 2 million and 2.5 million individual blocks of stone. That is not just a large pile. That is a mountain systematically disassembled and reassembled into a perfect geometric shape. The average weight of one of those limestone blocks is about 2.5 tons, roughly the same as a modern pickup truck. But that is just the average. The real logistical nightmares are the exceptions, the stones that defy belief. Deep inside the pyramid, forming the ceiling of the king's chamber, are 9 colossal granite beams. Each one of these ceiling stones weighs approximately 80 tons. To put that into a modern perspective, that is heavier than a fully loaded semi-truck and trailer. And these granite monoliths did not come from a local quarry. They were sourced from Aswan, a site over 500 miles up the Nile River from Giza. So the challenge becomes breathtakingly clear. It was not just about moving a mountain of stone. It was about moving specific, enormous pieces of that mountain across a distance greater than the length of the entire United Kingdom. This was the core problem, a physical equation of mass times distance, written on a landscape scale. How do you solve an equation where the variables weigh 80 tons and the distance is measured in hundreds of miles? The answer would not be found in a single brilliant invention, but in a system, a living, breathing network of planning and execution that transformed an impossible dream into solid, enduring reality. The journey of every monumental stone begins not with a journey but with a separation. Before a single block could be hauled or floated, it first had to be persuaded to leave the living rock. This is where the logistics chain truly starts, at the raw, scarred landscapes we call quarries. Here, we find the first fingerprints of the ancient system, in the very techniques used to break a mountain into manageable pieces. The evidence is still etched into the bedrock at places like Aswan in Egypt, home to the famous Unfinished Obelisk. This colossal needle of granite, still attached to the bedrock, is a frozen snapshot of the quarrying process. Around it, you can see the precise channels cut by workers using nothing more than stone pounders. They would hammer a line of holes along the intended fracture line, then drive wooden wedges into them. When the wedges were soaked with water, they would expand with tremendous force, cleanly splitting the granite along a predetermined plane. It was a patient, brilliant application of simple physics. For softer stone like limestone, the method was often more dramatic. At the quarries of Tura, which supplied the fine white casing for the pyramids, workers might use a technique called fire setting. They would build a fire directly against the rock face, heating the stone intensely, and then suddenly douse it with cold water. The rapid thermal shock would cause the rock to crack and spall, creating weaknesses that could be exploited with levers and chisels. Once a block was free, the shaping began right there at the quarry site. Using harder stone tools and abrasive sand, teams would rough cut the block to its approximate size and shape. This was a critical logistical decision. Removing excess weight here at the source meant moving a lighter, more manageable object for hundreds of miles. It turns the quarry from just a source of material into the first stage of factory production, where raw material was partially processed into a standardized component. The Unfinished Obelisk, however, tells another, more profound story. It cracked during extraction and was abandoned in place. This single failure is a powerful testament to the immense risk involved. A flaw hidden deep within the stone could mean months of labor and the investment of an entire team lost in an instant. It underscores that quarrying was not just a matter of brute force. It was a high-stakes operation of geology, planning, and skilled craftsmanship. The quarry was not just a hole in the ground. It was the first and most critical node in a vast supply network. But freeing the stone was only the beginning of the real challenge. You now had an 80-ton component sitting in a quarry and a construction site 500 miles away waiting for it. This gap between source and destination is where logistics becomes a story of people. We often picture this labor as an endless, anonymous chain of enslaved individuals driven by the whip, an image popularized by films and older histories. But the emerging evidence paints a far more complex and fascinating picture. The true machinery behind moving mountains was not built on cruelty, but on organization. Think about the sheer scale of coordination required. At Giza, during the peak of pyramid construction, historians estimate a workforce of perhaps 20,000 individuals was active at any one time. These were not just haulers. This was a society in miniature, requiring an entire support system to function. Recent archaeology at the Giza Plateau has uncovered the buried remains of vast, planned settlements for these workers. These were not slave pits, but structured villages with barracks, bakeries, breweries, and even medical facilities. The discovery of thousands of cattle and fish bones tells us these crews were fed a diet rich in protein, essential for sustaining the immense physical effort of construction. This changes everything. Feeding 20,000 people a daily meal of meat and bread is a logistical operation rivaling the movement of stone itself. It required its own supply chains for grain, livestock, and fish, its own teams of bakers and butchers, and its own system of distribution. Managing this workforce was a feat of social engineering. Research suggests much of the labor was seasonal, drawn from farming communities during the Nile's annual flood, when agricultural work was impossible. These farmers would contribute their labor as a form of national service, often organized into crews with names like Friends of Khufu or the Drunkards of Menkaura, groups that took pride in their work. They were likely skilled in specific tasks, from precise stone dressing to the complex rope and lever systems used for positioning blocks. The overseers of this endeavor were not just taskmasters, but administrators, engineers, and quartermasters. They had to track tools, manage ration distributions, assign crews to specific projects, and maintain morale over decades. This human system, this living network of specialized skills and coordinated labor, was the true engine that powered the megaprojects. The stones are the testament, but the villages, the ration lists, and the carefully planned infrastructure are the story. They reveal that before you can move a mountain, you must first build a city to support the people who will move it. Once the stone was shaped and the workforce assembled, the next equation was pure physics. How do you translate human strength into the movement of an object that weighs as much as a house? For land transport, the ancient answer was both elegantly simple and brutally demanding. The most fundamental tool was the sledge, a robust wooden platform that distributed the massive weight of a stone block across a wider surface area. We have direct visual evidence of this from Egyptian tomb paintings, which show detailed scenes of colossal statues being towed on sledges by large teams of workers. But a sledge dragging directly on sand or earth creates immense friction, a force that would require an impossibly large number of people to overcome. The ancient engineers found clever ways to cheat friction. The tomb paintings often show a person standing at the front of the sledge, pouring what appears to be water or a thin slurry onto the ground just in front of the runners. For decades, this was thought to be a ceremonial act. Experimental archaeology proved it was a brilliant practical solution. A team from the University of Amsterdam recreated the scene, placing a replica sledge on dry sand. They found the required pulling force was enormous, but when they added just the right amount of water to the sand, the grains bonded together, creating a firm, slick surface. The friction coefficient dropped by half, meaning the same team could pull twice the weight. It was not magic, it was applied physics, turning the desert itself into a temporary roadway. Another widespread method involved the use of rollers. Teams would place a series of logs or rounded stone cylinders under the sledge or the block itself. As the load was pulled forward, workers at the back would constantly retrieve the rollers that emerged and run them to the front, creating a continuous, moving track. This method transformed sliding friction into the much lower rolling friction, a monumental efficiency gain. Yet even with these innovations, the scale of effort remains almost incomprehensible. Moving an 80-ton granite block on a lubricated sledge might still require a coordinated team of several hundred individuals, all pulling in unison to the rhythm of a foreman's chant or drumbeat. The limitations were severe. This method was excruciatingly slow, vulnerable to uneven terrain, and required an immense, readily available supply of labor and materials, like water or timber for rollers. It was a solution for shorter, controlled distances, a testament to what could be achieved through sheer coordinated human power when the will of a civilization was concentrated into a single, earth-shaking pull. A lubricated path was a temporary fix, but for a project spanning decades, you need permanent infrastructure. This is where ancient logistics shifted from clever tricks to outright civil engineering, building not just monuments, but the specialized highways that led to them. The most famous examples are the colossal earthen ramps proposed for the pyramids themselves. While no definitive ramp structure has survived the millennia, the architectural necessity for one is undeniable. To raise millions of blocks to a height of over 480 feet, some form of inclined plane was essential. Historians and engineers have debated the exact design for centuries. One prominent theory suggests a long, straight ramp built directly against one face of the pyramid, growing in length and height as the structure rose. The math, however, becomes daunting. To maintain a manageable gradient for teams pulling heavy sledges, perhaps a slope of 10% or less, such a ramp would have needed to be over a mile long by the time it reached the pyramid's peak. The volume of material in the ramp itself could have rivaled that of a third of the pyramid. A more efficient, though complex, alternative is the idea of a spiraling ramp, wrapping around the pyramid's sides as it ascended. This would be shorter and require less fill material, but it would have created difficult corners for hauling teams to navigate, and would have obscured the builder's sightlines for maintaining the structure's precise geometry. Regardless of the specific design, the concept is a testament to long-term planning. Building the ramp was a megaproject before the megaproject, a massive investment of labor solely to create a pathway for all the labor to come. More tangible evidence of this transport infrastructure survives elsewhere. In the Fayum region of Egypt, archaeologists have uncovered remnants of extraordinary paved roads, built specifically for moving colossal stone statues from the quarries to the Nile. These were not simple dirt tracks, they were engineered roadways constructed from massive limestone blocks fitted together to form a smooth, durable surface capable of bearing unimaginable weight. The roads often featured curbstones and were cambered or slightly arched to shed water and prevent erosion. Most importantly, their gradients were carefully calculated. The builders would survey the landscape, choosing the gentlest possible route, and when necessary, cutting through hills or building up low areas to maintain a consistent, shallow slope. This was not just about making the haul easier, it was about making it possible. A sudden steep incline could stop an 80-ton load in its tracks, risking the stone, the sledge, and the safety of the entire crew. These roads represent a permanent investment in logistics, transforming the chaotic landscape into a predictable, reliable conduit for stone. They tell us that for these ancient engineers, the journey was not an obstacle to be overcome once, but a process to be perfected, standardized, and etched permanently into the earth itself. Roads and ramps solved the problem of horizontal distance, but they all led to a final, vertical wall. The true climax of ancient logistics was not the haul, but the lift. How do you take an object weighing dozens of tons and raise it hundreds of feet into the air with perfect precision? This final act required a different kind of genius, one that understood how to cheat gravity itself using the fundamental principles of physics. The ancient builders mastered simple machines, tools that trade distance for force, allowing a small team to achieve what would otherwise require an army. The most iconic of these is the lever, a long, sturdy timber placed under a stone with a pivot point or fulcrum. Close to the load transforms a downward push on the far end into an immense upward force. By placing a series of wooden blocks or cribbing under the stone as it was lifted incrementally, a crew could walk a colossal block upward, step by wooden step, in a controlled, stable ascent. This method was likely essential for the final precise positioning of the massive granite beams in the pyramid's burial chambers, but for the relentless, repetitive lifting required to build the pyramid's core, a more continuous system was needed. This brings us to one of the most compelling modern theories, the internal ramp hypothesis. Proposed by the architect Jean-Pierre Houdin, this idea suggests that the Great Pyramid was built using a spiraling ramp, but one that was built inside the structure itself, corkscrewing upward within the growing walls. As the teams hauled a block up this enclosed, sloping tunnel, they would always be pulling on a level surface inside the monument, a far more efficient and stable method than dragging a sledge up an exposed, earthen ramp hundreds of feet in the air. The finished pyramid would then entomb its own construction roadway, a hidden skeleton of effort locked within the stone. For the most audacious lifts of all, the raising of giant obelisks, the ancients combined several principles into a breathtaking spectacle. Evidence suggests they would first haul the monolithic needle to the base of a specially constructed, massive earthen ramp, positioning its base at the edge of a deep foundation pit. The obelisk would then be pulled up the ramp until it pivoted over the pit, its base beginning to descend into the waiting socket. With its weight now partially supported by the far edge of the pit, teams could use ropes and the gradual removal of sand from a chamber beneath the stone to lower it with control, guided by timber frameworks. It was an operation of breathtaking nerve, a slow-motion ballet of gravity, counterweight, and human guidance. These were not acts of magic but of profound understanding. By using the incline of a ramp to trade a long, easy pull for a steep, impossible lift, or by using a lever to multiply the force of a few individuals, the builders turned fundamental physics into the ultimate labor-saving device. The monument we see is the end result. The invisible machinery of levers, ramps, and pivots is the forgotten engineering, the silent partner in every ancient wonder that reaches for the sky. Yet for all the ingenuity of ramps and levers, the most powerful machine in the ancient world required no construction at all. It was the river. Before a single stone could be lifted into place on the Giza plateau, it first had to complete a journey of hundreds of miles, a journey made possible only by water. Rivers like the Nile, the Euphrates, and the Tigris were not just sources of life. They were the original superhighways, the logistical backbones upon which empires were literally built. Moving an 80-ton block of granite overland for 500 miles would have been a logistical nightmare of unimaginable proportions, consuming vast amounts of labor and time. But floating that same block on a barge down the Nile transformed the equation entirely. Water supports weight, eliminating the crushing force of friction. A single boat, powered by the current and a few sails, could carry the equivalent load of thousands of laborers pulling sledges across the desert. This is why the map of ancient megaprojects is also a map of river networks. In Egypt, the major quarries were almost all Nile adjacent. The limestone came from Tura, just across the river from modern Cairo. The red granite came from Aswan, located at the Nile's first cataract. The quarries were not chosen solely for the quality of stone, but for their access to this liquid roadway. The process began at the quarry's edge, where engineers faced another monumental task: loading. How do you transfer an object heavier than a locomotive from the bank onto a wooden vessel without capsizing it? Evidence suggests the use of cleverly designed canals or basins dug right up to the quarry face. Workers could partially float a barge by letting water into this basin, maneuver it directly alongside a prepared stone resting on a sledge, and then use levers, ropes, and counterweights to carefully shift the mass from land to water, a delicate operation of balance and control. Once secured, the journey could begin. The Nile's predictable northward current would carry the heavily laden barge downstream toward the construction site with minimal effort. For the return trip or for journeys upstream, crews could raise sails to catch the prevailing northerly winds, harnessing nature's engine in both directions. The ancient builders even turned the river's annual cycle into a tool. The Nile flood, which inundated the land each year, was not just an agricultural event, it was a logistical opportunity. During the high water period, channels and canals that were dry for most of the year became navigable. Builders could float barges loaded with stone much closer to a desert construction site, dramatically reducing the final, arduous overland haul. This was a civilization thinking in sync with its environment, using the rhythm of the seasons as part of its construction calendar. In Mesopotamia, the story was similar, with the Tigris and Euphrates serving as the vital arteries for moving the stone and timber that cities like Ur and Babylon required. The river did not just carry stone, it carried the entire possibility of monumental architecture. Without this natural highway system, the pyramids would have remained a dream in the sand, and the story of ancient logistics is, in many ways, the story of learning to listen to the flow of the water. The river was a highway, but the sea was an ocean of risk. For civilizations whose ambitions stretched across the Mediterranean, moving stone was no longer a matter of floating downstream. It became a battle against waves, weather, and the immense, unforgiving weight of cargo that could sink a ship in an instant. This challenge birthed a new class of vessel and a new frontier in ancient logistics: maritime megalith transport. The Romans, masters of infrastructure, faced this problem head-on as they built their empire. To supply marble for the grand forums, baths, and temples of Rome, they needed a reliable pipeline from distant quarries. The answer was the naves lapidarii, the stone-carrying ships. These were not standard cargo vessels adapted for a heavy load. They were engineered from the keel up for one terrifying purpose. Historical accounts and scattered wreck evidence suggest these ships were massive, broad-beamed, and incredibly sturdy. Their hulls were reinforced with extra internal bracing to withstand the constant, crushing stress of hundreds of tons of stone shifting in a swell. They likely had multiple, closely spaced masts to provide the power needed to move such a dense mass through the water. But the true test of the system came at the beginning and end of the voyage, at the quarry port and the destination dock. Without steel cranes or hydraulic lifts, loading a 50-ton column of marble was an operation of elegant physics. At quarries like those at Carrara in Italy or Mons Claudianus in Egypt, engineers often built stone loading piers that extended into deep water. A common method involved using the principle of the counterweight. The stone block would be carefully levered onto a wooden cradle on the pier. This cradle was attached by ropes to a large wooden frame structure that pivoted over the water. On the other side of the pivot, a container or basket would be loaded with heavy stones, acting as the counterweight. By carefully releasing the brake on this system, the counterweight would descend, swinging the stone block out over the water and lowering it gently down onto the waiting ship's deck where it could be secured. Unloading at Rome's port of Ostia required a similar setup in reverse, a delicate dance of balance to transfer the mountain from sea to land. This was infrastructure built for permanence, turning a port into a specialized industrial machine. But the Romans were not the only ones to brave the open water with stone. Far earlier, on the islands of Malta, a Neolithic culture with no metal tools built a network of monumental stone temples using massive limestone blocks. Their quarries were local, but the sea still played a role. Some theories suggest that during periods of higher sea levels, builders could have used simple, buoyant rafts made of logs or bundles of reeds to float the smaller megaliths along the coastline, skirting difficult terrain. The real maritime mystery, however, lies with cultures like the Greeks, who transported enormous blocks for temples and statues across the Aegean. A famous example is the unfinished Kuros statue, a giant figure of a youth found still lying in its quarry on the island of Naxos. It was clearly intended for export, but its size, over 30 feet long, poses a staggering question. What kind of vessel could have carried it, and how would they have loaded something of that shape and weight without it tearing through the hull? The likely answer involves a technique called rafting. The stone itself might have been partially shaped into a form that could act as its own hull, or it could have been lashed between two long, parallel boats to create a stable, catamaran-like transport. These voyages were gambles. A sudden storm, a snapped lashing, or a hidden reef could mean the loss of a year's labor and the lives of the crew. Yet they undertook them, driven by a vision of a temple on a distant shore or a statue in a foreign city square. The maritime transport of stone represents the ultimate expansion of the logistical network, pushing it beyond the safety of rivers and into the realm of the unpredictable. It tells us that for these cultures, the value of the finished monument was worth the profound risk of trusting a mountain to the mercy of the sea. The sea was a formidable adversary, but the Romans did not just brave it, they organized it. If earlier civilizations mastered the art of moving mountains, the Roman Empire perfected the science of moving continents. Their approach transformed logistics from a series of brilliant projects into a permanent, humming industrial machine, powered by standardization, infrastructure, and bureaucracy. Consider the very stones they used across the empire, from the walls of Roman forts in Britain to the temples of North Africa. You see a signature style known as opus quadratum. This was not just an aesthetic choice, it was a logistical one. It involved cutting stone into uniform, rectangular blocks of consistent dimensions. Why does this matter? Because a standardized block is a predictable unit. It can be loaded, shipped, and assembled by any trained crew, anywhere in the empire, using the same set of techniques and measurements. It turned construction into a kind of kit, where interchangeable parts could be produced in bulk at a quarry, and then shipped to multiple building sites. This system reached its peak with the empire's insatiable appetite for marble. The gleaming white stone from the quarries at Carrara in Italy became the ultimate status symbol, adorning forums, baths, and palaces. But Carrara was just one node in a vast network. The Romans sourced green marble from Greece, purple porphyry from the deserts of Egypt, and yellow stone from North Africa. Each quarry was a specialized factory, often state-controlled, producing not just raw material but pre-finished elements, columns, capitals, and slabs, all cut to imperial specifications. This network was fed by the empire's greatest physical achievement, its infrastructure. The famous Roman roads, built for the swift movement of legions, also became the arteries of commerce, allowing heavy wagons loaded with stone to travel in all weather. More critically, they built and maintained an unparalleled system of ports, from Ostia at the mouth of the Tiber to Alexandria in Egypt. These were not simple harbors, but complex industrial hubs with massive breakwaters, deep water berths, and the specialized loading cranes we discussed earlier. A block quarried in Egypt could be loaded onto a ship, sailed across the Mediterranean, unloaded at Ostia, transferred to a barge for the trip up the Tiber, and then carted the final distance to a construction site in the heart of Rome, all on purpose-built infrastructure. Yet stone and roads are inert without coordination. The true genius of the Roman system was the invisible layer that managed it all, the bureaucracy. At the heart of this was the Cursus Publicus, the Imperial postal and transport service. While primarily for government communication, this system also managed the movement of official goods and personnel. It provided a network of way stations with fresh horses, wagons, and storage facilities at regular intervals along every major route. For a state-sponsored building project, this meant a pre-existing framework for organizing supply convoys, sheltering crews, and ensuring that materials kept moving on schedule. Imperial officials, the procurators, were stationed at key quarries and ports to oversee production, manage inventories, and handle the complex paperwork of contracts and shipments. This level of organization meant the empire could undertake projects on a previously unimaginable scale simultaneously, building a frontier wall in northern Britain while also erecting a monumental column in Rome, both fed by stone from distant, managed quarries. The Roman achievement was not in inventing the wheel or the lever, but in building the system that made sure the right wheel and the right lever were always in the right place at the right time. They turned logistics from an art into an empire's heartbeat, but across the Channel and centuries earlier, a different kind of mystery was taking shape on the Salisbury Plain. The story of Stonehenge begins not with imperial roads but with a profound absence. The society that built it had no wheels, no metal tools, and no domesticated animals for heavy hauling. Yet they moved stones that weighed up to 50 tons across a landscape of rolling hills and dense forests. This is the megalithic mystery, a logistical puzzle that seems to defy the very tools we assume are necessary. The central question is stark: how do you move a mountain when you lack everything we consider essential for the task? The stones themselves tell a divided story. The iconic outer circle and trilithons are made of sarsen, a hard sandstone. These colossal blocks, the largest weighing around 50 tons, were sourced locally from the Marlborough Downs about 20 miles to the north. 20 miles may not sound far, but for a Neolithic community moving a 50-ton slab, it was a world away. The smaller, inner bluestones, however, present the deeper enigma. Their geological fingerprint points unequivocally to the Preseli Hills in southwest Wales, a distance of over 150 miles. This fact alone ignited a century of debate, splitting theories into two opposing camps. One argues for nature as the primary mover. The glacial theory suggests that during the last ice age, advancing ice sheets plucked these bluestones from the Welsh hills and carried them eastward, depositing them much closer to Salisbury Plain. In this scenario, the builders merely collected locally available, exotic stones. The other camp argues for human agency, for a deliberate, monumental effort to transport these stones across the breadth of Britain. Recent geological studies have sharpened the debate. While some glacial movement is possible, the specific types of bluestones at Stonehenge appear to come from very precise, exposed outcrops in the Preseli Hills, not from a scattered glacial deposit. This points toward a deliberate quarrying operation. Archaeologists have even identified probable Neolithic quarry sites at Craig, Rose Wyfellen, and Carn Godog in Wales, where they found stone tools, charcoal from fires used to fracture the rock, and even artificial stone platforms that could have been used for loading. If humans moved them, the next question is how. The overland route is a story of terrain and traction. Without wheels, the likely method was a combination of sledges, rollers, and leverage. A team from University College London conducted a famous experiment in the 1950s. Using a concrete replica of a bluestone weighing around 1 ton, they placed it on a wooden sledge and pulled it along a track of greased wooden rollers. They found that on level ground, a team of around 120 people could move the stone at a slow but steady pace. Scaling this up for a 4-ton bluestone, let alone a 50-ton sarsen, would require a coordinated community effort numbering in the hundreds, pulling in unison to the rhythm of drums or chants. The journey would have been a seasonal pilgrimage, likely undertaken in winter when the ground was firmer and agricultural work was minimal, but the most compelling theories often involve water. A potential route from Wales could have combined land and river travel. Stones might have been dragged down from the hills to the nearby rivers, then loaded onto rafts or lashed between dug-out canoes for a coastal journey. They could have sailed up the Bristol Channel and then eastward along river systems like the Avon, getting them within a final, shorter overland haul to the plain. This waterborne theory turns the Severn estuary into a Neolithic highway. It suggests these builders were not just terrestrial engineers, but coastal navigators who understood how to use currents and tides to their advantage. The truth likely lies in a hybrid of these methods, a testament to a society that viewed the entire landscape, from mountain to river to sea, as a single, integrated system for achieving the impossible. They may not have had the Roman bureaucracy, but they possessed something equally powerful, a shared cultural vision so strong it could convince a community to spend generations moving mountains, one back-breaking pull at a time. Theoretical routes and ancient paintings only tell half the story. To truly understand the physical reality of moving a megalith, you have to get your hands dirty, to feel the strain of the ropes and the stubborn grip of the earth. This is where experimental archaeology enters the scene, a field where scholars don lab coats and work gloves to test history with their own hands. Some of the most revealing experiments have focused on a single, relentless enemy, friction. How do you reduce it enough to make an impossible pull merely difficult? One provocative idea involves not water, but ice. Could ancient builders have created artificial ice tracks to glide stones across? A team inspired by Inuit practices once tested this in a cold climate, spraying water on a path to form a slick, frozen runway for a sledge. The results were dramatic, showing a drastic reduction in pulling force. However, for civilizations in temperate regions like Egypt or Britain, maintaining long ice tracks, especially in a desert climate, presents an enormous practical challenge. The required volume of water and the constant labor of refreezing it make it an intriguing but unlikely solution for most large-scale projects. A more widely tested and plausible method involves the greased wooden track. This brings us to the famous experiments conducted for public television documentaries, where researchers and volunteers attempted to move a concrete replica of a pyramid block. They constructed a pathway of wooden rails, smoothing the surface and coating it with a slurry of water and clay as a lubricant. A large wooden sledge was placed on these rails, and teams of volunteers took up long ropes. The initial pull was always the hardest, overcoming static friction. But once the sledge began to move, the force required dropped significantly. These practical tests yielded crucial data. They suggested that on a prepared track, a 1-ton block could be moved by a crew of about 12 to 20 people. Scaling up for a 2.5-ton pyramid block, a crew of 50 might be feasible. For a 50-ton sarsen stone at Stonehenge, the numbers ballooned to several hundred pullers, a massive but not inconceivable communal effort. The experiments also revealed the critical, unseen work. The real time was not spent in the pull itself, but in the preparation, felling trees, milling them into rails, transporting and placing them, and constantly maintaining the lubricated surface. This was the hidden 90% of the labor. A single journey might require a portable road built just inches ahead of the stone, a disposable infrastructure consumed by its own purpose. Perhaps most importantly, these tests highlighted the role of leadership and rhythm. Moving a multi-ton object is not a sprint, it is a synchronized, plodding march. A crew needs clear commands, a steady drumbeat or chant to coordinate their heaves, and a system for rotating tired pullers without losing momentum. The experiments proved the physics was sound, but they also underscored that the true machinery was social, a well-organized community acting as a single, powerful engine. The sledge, the rails, and the lubricant were the tools, but the coordinated will of the people was the fuel. Human strength has its limits, a truth that echoes in the aching pull of every rope. Yet in the ancient world, another source of power walked on four legs, waiting to be harnessed. The integration of draft animals into the logistics of stone was not a universal step in history, but a geographical and cultural lottery that dramatically reshaped what was possible. In regions blessed with large, trainable beasts, the equation of mass and distance was rewritten. The sturdy ox, with its immense pulling power and patient temperament, became the diesel engine of the ancient world. In the Indus Valley civilization, as early as 2,500 years before the Common Era, evidence suggests the use of oxen for transporting heavy goods. While direct evidence for moving megaliths is scarce, the presence of standardized brick weights and extensive trade networks implies a mastery of bulk transport that would have relied heavily on animal power. Later, the Romans systematized this on an industrial scale, employing vast teams of oxen to pull wagons laden with stone along their famed roads. A single ox team could pull a load equivalent to dozens of human laborers, and they could do it for longer without the need for complex rationing systems that human crews required. This was a force multiplier of staggering proportions, but the most awe-inspiring application came in South Asia, where civilizations had access to the ultimate living machine, the elephant. With its colossal strength, intelligence, and sure-footedness, an elephant could perform tasks impossible for oxen. Historical accounts from India and Southeast Asia describe elephants being used not just to pull stones, but to precisely position them. Guided by a mahout, an elephant could use its tusks and trunk to nudge massive blocks into alignment with a delicacy that belied its power. An elephant did not just replace a team of oxen, it replaced an entire system of ramps and levers for certain final placements, merging transport and construction into a single, fluid act. This access to animal power created a divergent path in the story of logistics. Contrast this with the builders of Stonehenge in Neolithic Europe or the early pyramid builders in Egypt. In Britain, the society that erected the Great Saracens had no domesticated animals suitable for heavy hauling. Their power source was the communal human chain, a testament to social cohesion. In early dynastic Egypt, during the initial construction of the major pyramids, the domesticated donkey was present and used for carrying lighter loads, but the water buffalo and the horse had not yet been introduced. The iconic image of thousands of workers pulling on ropes in tomb paintings may be literal, because for moving the largest blocks, human coordination was still the primary engine. The adoption of the horse and more powerful cattle breeds in later Egyptian periods undoubtedly eased later monumental works, but the foundational wonders were built largely on human sinew. This divide reveals a profound truth. The scale of an ancient megaproject was not just a reflection of a society's ambition, but of its ecological toolkit. Where the ox or elephant was available, the logistical ceiling rose exponentially, allowing for the movement of even larger stones over even longer land routes. Where they were absent, the achievement rests even more heavily on the breathtaking organization of human community. The silent, patient strength of the beast did not diminish the human accomplishment. It simply changed the nature of the partnership, asking not just how a society could organize itself, but how wisely it could harness the world around it. A flawless system can be undone by a single, hidden weakness. For all their planning and power, the ancient engineers were forever at the mercy of the stone itself. The most powerful testament to this vulnerability is not a towering success, but a magnificent failure still lying in its granite bed in Aswan. The unfinished obelisk offers a frozen moment of crisis, a forensic snapshot of the immense risk embedded in every megalithic project. If completed, it would have been the largest single piece of stone ever carved by human hands, a needle of red granite reaching 137 feet into the sky and weighing an estimated 1,200 tons. Today, it remains a ghost of that ambition, a colossal shape partially freed from the living rock, its lower side still seamlessly attached to the bedrock. The reason for its abandonment is etched clearly into its surface, a network of deep, catastrophic cracks that appeared during the final stages of extraction. This was not a surface blemish, but a fatal flaw running deep into the heart of the stone, rendering the entire monolith useless for its purpose. The story this fracture tells is one of staggering investment suddenly rendered void. Consider the labor already expended. Teams would have spent months, perhaps even years, painstakingly carving the trench around the obelisk's outline using nothing but stone pounders. They would have prepared the entire logistical chain, the roadways, the ramps, the colossal sledges and barges needed for its transport down the Nile. A workforce of hundreds, maybe thousands, was mobilized, fed, and housed for this single object. And then, in a moment, a crack. The sound of splitting granite would have signaled not just the failure of the stone, but the collapse of an entire economic and social undertaking. All that coordinated effort, all that consumed resource, was now a total loss. This single abandoned project lays bare the razor's edge on which these logistics systems operated. Quarrying was not a guaranteed process, it was a high-stakes gamble with geology, a hidden vein of weakness, an unseen stress point from millennia of geological pressure could lurk within what appeared to be perfect stone. The builders had no X-ray vision, no modern seismic testing. They relied on experience, careful observation of the rock face, and an element of faith. The unfinished obelisk demonstrates that for all their system building, the ancients were never fully in control. Their entire logistical network, from the quarry foreman to the barge captain, depended on the integrity of a material they could only judge from the outside. This failure, however, is far more instructive than any success. It shows us the true cost of ambition, measured not in gold, but in the incalculable investment of human time and hope that could vanish with a single, echoing crack. It forces us to see these perfect monuments not as inevitable, but as the survivors of a relentless process of trial and terrifying error, where one flaw in the stone could mean the end of a dream. The calendar was as crucial a tool as the lever or the sledge. Ancient logistics did not operate on a relentless, industrial clock, but in harmony with the rhythms of the earth itself. The most powerful force in their planning was not a king's command, but the predictable turn of the seasons, which dictated both the availability of labor and the very landscape they had to cross. This synchronization transformed impossible tasks into seasonal routines, embedding monumental ambition within the natural cycle of life. The Nile River provides the clearest example of this brilliant timing. For most of the year, the stone barges from Aswan would sail north with the current, but their final approach to a desert construction site like Giza presented a last-mile problem. How do you get a 50-ton block from the riverbank to the plateau, a distance that could still be several miles of soft sand and rising ground? The answer arrived with the annual inundation. Each summer, fed by rains far to the south, the Nile would overflow its banks, spreading a shallow layer of water across the floodplain. This was not a disaster, it was an opportunity. Engineers would dig canals from the main river channels directly toward the building site. When the floodwaters rose, these canals would fill, becoming navigable waterways. A barge loaded with stone could now sail or be towed much closer to its destination, sometimes right to the very edge of the rising desert. This strategic use of the flood season effectively extended the river highway, shrinking the final, grueling overland haul from miles to perhaps only a few hundred yards. It turned the most challenging leg of the journey into a simple float. The entire construction schedule for projects like the pyramids was likely built around this annual aquatic gift, with quarrying and shaping happening year-round, but the mass transport of the heaviest stones concentrated into the few months when the water was highest. This was logistics as a form of environmental listening, using the planet's own cycles as a primary piece of construction equipment. The seasonal rhythm also governed the human engine. These societies were predominantly agricultural. The same hands that planted and harvested grain were needed to pull ropes and haul sledges. A permanent, year-round workforce of tens of thousands dedicated solely to construction would have crippled the food supply. Instead, the system leveraged downtime. In Egypt, the Nile flood that aided transport also rendered the fields untouchable for months. With farming impossible, a vast pool of labor became available. Farmers who were already physically strong and accustomed to communal work would be mobilized for state projects. This was not necessarily a burden, but a reciprocal part of the social and economic cycle. They contributed their labor, were housed and fed by the state from stockpiled grain, and likely received other forms of compensation. When the waters receded and the fertile silt was ready for planting, they would return to their fields. This cyclical mobilization meant the workforce was renewable, sustainable, and drawn from a population that was not permanently alienated from its livelihood. We see similar patterns elsewhere. In Neolithic Britain, the major efforts at Stonehenge were likely winter projects, when the ground was firmer for hauling and farming demands were minimal. This strategic timing reveals a profound intelligence. The ancient planners were not fighting against the constraints of their world. They were weaving their ambitions into its very fabric. They used the flood as a highway and the agricultural off-season as a labor reservoir. The monument that resulted was not just built from stone, but from the deliberate, patient alignment of human effort with the turning of the year. The silent stones do not speak of the voices that commanded them, yet behind every perfectly placed block was a mind that held the entire project in its thoughts, a person who could see the finished monument long before the first stone was cut. These were the ancient project managers, the invisible architects whose true tools were not chisels but organization and foresight. In Egypt, we catch glimpses of them in surviving titles, grand and specific, like the overseer of all the king's works. This was not a ceremonial role. It was a position of immense practical authority, the ancient equivalent of a chief executive officer for the world's largest construction firm. Beneath this supreme overseer stretched a detailed hierarchy, a pyramid of responsibility mirroring the stone one being built. There would have been overseers of the quarries, masters of the transport barges, chiefs of the hauling crews, and foremen for the masonry teams. Each layer managed its own domain, reporting problems upward and translating grand directives into specific, daily tasks. This structure was essential for decentralization. The quarry master at Aswan did not need to consult the king about a cracked obelisk. He had the authority to make a decision based on his expertise, keeping the complex machine running without constant referral to the top. But how did this hierarchy plan for a project spanning decades, a timeline longer than a single human lifespan? They likely operated without the detailed blueprints and Gantt charts of a modern engineer. Their plans were a combination of physical models, established architectural ratios, and deep, accumulated experience passed through oral tradition. A master builder would know, from a lifetime of work and the teachings of his predecessors, that a ramp must have a slope no steeper than 1 in 10, that a certain type of mortar set best in the dry season, or that transporting granite was only feasible during the high Nile. This was knowledge embedded in practice, not written in manuals. Resource allocation was managed through an almost intuitive understanding of scale. The overseers knew how many men it took to pull a sarsen stone a mile in a day, how much bread and beer was needed to feed that crew, and how many scribes were required to tally the incoming limestone blocks from Tura. They thought in ratios and rhythms. If you have 1,000 masons dressing stone, you will need 5,000 haulers to keep them supplied, and 2,000 bakers and brewers to keep everyone fed. This was project management as a living tradition where the plan resided not on papyrus, but in the collective memory and skilled judgment of a professional class. They maintained continuity through apprenticeship, ensuring that the son of a quarry overseer learned not just how to spot good stone, but how to manage the teams that extracted it. The true monument they built was this system itself, a resilient, adaptable structure of human coordination that could outlast any single ruler and turn a visionary dream into a mountain of enduring order. This invisible network only makes sense when we follow a single stone. So let's trace the journey of one massive block, from its birth in the earth to its final resting place in a pyramid's core, and watch the entire system come to life. Our story begins in a limestone quarry at Tura, where the sun beats down on a team of specialists. Using stone tools and fire setting, they have spent weeks isolating a perfect block from the living bedrock. Once free, it is rough-shaped by masons right there at the site, its excess weight carved away to ease the coming journey. This is the first handoff from quarrymen to the transport crew. A team arrives with a massive wooden sledge. Using levers and ropes, they painstakingly coax the multi-ton block onto its wooden carrier. Now the real coordination begins. A foreman surveys the prepared route, a pathway of wooden rails already laid toward the Nile. As dozens of pullers take up ropes, another worker walks ahead, pouring water to create a slick, hardened surface on the track. Their synchronized heave, guided by a rhythmic chant, sets the stone in motion, inching toward the river. Days later, the block reaches a specially built loading dock on a canal fed by the Nile. Here, the land team's work ends and the river team takes command. A broad, flat-bottomed barge is floated into the dock basin. Using a counterweighted wooden crane, dock workers carefully transfer the stone from sledge to barge deck, securing it with ropes. The handoff is precise, a delicate transfer of responsibility and weight. With the stone secured, the barge captain waits for the signal. His vessel is one of dozens in a seasonal convoy, all timed to the annual flood. When the water is high enough, the convoy sets sail, carried north by the current and pushed by the wind, a slow, stately procession down the liquid highway toward Giza. Weeks of river travel later, the convoy arrives at a port canal dug right to the edge of the desert plateau. It is the peak of the inundation, and the water has extended the Nile's reach. The barge is unloaded by another crane crew, placing the block onto a fresh sledge waiting on a paved road. This is the final land haul, the last mile. A new pulling crew, perhaps hundreds strong, takes the ropes. They drag the stone up a long, gently sloping ramp made of packed earth and rubble, a ramp that grows with the pyramid itself. Each pull brings it closer to the summit. Finally, at the working level high on the pyramid's face, the masons take possession for the last time. They perform the final dressing, smoothing the stone to exact specifications. Then, using levers, ropes, and wooden cribbing, a small, skilled team guides the block into its predetermined spot, a perfect fit in a growing geometric puzzle. The journey is complete. What we have just followed is not a single task but a relay race of specialized labor. The quarry team never saw the masons on the plateau. The barge captain never met the ramp foreman, yet their work was perfectly synchronized, each phase dovetailing into the next because of a shared plan, a common language of measurement, and a hierarchy of oversight that made the handoffs seamless. The stone moved, but it was the system that flowed. But this intricate relay race of labor had a fuel, a fundamental requirement measured not in stone but in sustenance. We can admire the precision of the handoffs and the ingenuity of the ramps, yet to grasp the true scale of societal commitment, we must look at the energy budget. Every pull of a rope, every swing of a stone pounder was powered by calories harvested from the land. So let's perform a simple calculation to translate one stone's journey into the language of human energy. Take a single 2.5-ton limestone block for the Great Pyramid, the weight of a pickup truck. Modern studies in biomechanics suggest that moving such a load on a lubricated sledge over level ground might require a pulling force equivalent to about half its weight. To sustain that effort, a single laborer might burn well over 4,000 calories in a demanding workday, more than double what a moderately active person consumes today. Now scale that up. If a crew of 50 men is needed to move that one block, their collective daily energy expenditure soars to 200,000 calories just for the hauling crew alone. But the block's journey from Tura to Giza was not a single day's work. If the overland and river transport took, conservatively, 2 weeks, the cumulative caloric burn for that one stone's transport crew alone climbs into the millions. And this is just for moving it. We must also feed the quarrymen who extracted it, the masons who shaped it, the bakers who made the bread, the brewers who made the beer, and the administrators who coordinated it all. Suddenly, a single block is no longer just a piece of rock. It is a dense package of agricultural energy. This is where the societal commitment becomes staggering. To support a peak workforce of 20,000 individuals, each requiring perhaps 3,000 to 4,000 calories per day of hard labor, the project would have consumed tens of millions of calories every single day. This was not subsistence eating, this was high-performance fuel. The archaeological evidence of cattle bones and fish remains at the worker settlements tells us this diet was rich in protein and fat, essential for repairing muscle and sustaining endurance. Where did all this food come from? It flowed from the fertility of the Nile itself. The same annual flood that extended the transport canals also deposited the rich silt that created agricultural surplus. The pyramid, in a very real sense, was built from converted sunlight and river nutrients, transformed by farmers into grain and livestock, which was then collected, stored, and redistributed by the state to power the human machines on the plateau. This caloric lens reveals the monument as the pinnacle of an entire economic ecosystem. It makes the logistical system visible not just as a sequence of tasks, but as a vast metabolic engine. The true foundation of the pyramid was not the bedrock of Giza, but the accumulated agricultural wealth of the Nile Valley, carefully harvested, stored, and mobilized on a scale that would challenge many modern nations. To move a mountain of stone, you first had to grow a mountain of grain. The story of moving mountains was not a singular invention, but a melody played in different keys across the globe. While Egypt and Rome perfected the art of centralized, state-driven logistics, other ancient cultures composed their own solutions, often with a more decentralized, communal rhythm. Take the silent giants of Easter Island, the Moai. These towering stone figures, some weighing over 80 tons, were carved from volcanic rock at an inland quarry and then transported miles across the island to coastal platforms. The society here was not a vast empire with a bureaucratic machine, but a collection of clan-based groups. How did they move their statues? Oral traditions and modern experiments point to a method as simple as it is ingenious: walking the statues. By using a system of ropes to rock the moai back and forth, teams could, in a sense, make the statue shuffle forward in a controlled, swaying gait. This theory suggests a logistical effort built not on royal decree, but on the coordinated labor of individual family groups, each perhaps responsible for their own ancestor statue, moving in a slow, ceremonial procession across the landscape. It was a shared cultural goal achieved through distributed effort. Far to the east, in the Andes Mountains of Peru, another approach to stone defies belief. The fortress of Sacsayhuaman, built by the Inca, features walls constructed from colossal limestone blocks, some weighing over 100 tons, fitted together with a precision that leaves no space for a blade of grass. The Inca state was highly organized, but their environment presented a unique challenge: the steep, rugged terrain of the high mountains. Their solution likely involved a combination of immense manpower and a profound understanding of their materials. Without wheels or draft animals in the Americas, transport relied on human power. They may have used earthen ramps and ropes made from tough grasses, but their true secret might have been in the stone itself. Some researchers suggest the Inca mastered a technique of softening stone with plant acids, making it easier to shape and perhaps even reducing friction during transport, though this remains a topic of study. The logistics here were adapted to vertical geography, turning mountain slopes into quarries and using gravity as both an obstacle and a potential aid. Then we return to the enigma of Stonehenge on the Salisbury Plain. As we explored earlier, this Neolithic project presents the starkest contrast to the pharaoh's command economy. The society that built it had no written language, no central king, and no metal tools. The movement of the bluestones from Wales and the Saracens from 20 miles away points to a different kind of power, social cohesion. This was likely a collective endeavor driven by spiritual or seasonal significance, where clans from across southern Britain gathered periodically, perhaps during winter months or for festivals, to contribute their labor to a project that transcended any single chieftain. The logistics were not managed by an overseer of all the king's works, but by shared tradition and communal agreement. These global examples reveal a fundamental truth. The Egyptian model shows what is possible when a society concentrates its entire economic and administrative might into a single, decades-long project. The Roman system demonstrates how to industrialize that process across an empire, but the moai, the walls of Sacsayhuaman, and the stones of Salisbury Plain remind us that monumental ambition can also spring from a collective will, where the blueprint is held not in a royal archive, but in the shared identity of a people. Each culture faced the same brute equation of mass and distance, but they solved it with the tools, both physical and social, that their unique world provided. These systems we have traced from quarry to ramp are grounded in evidence we can see and touch. Yet hovering at the edges of this story are whispers of something else, theories of lost technologies that suggest the ancients possessed secrets we have yet to rediscover. These ideas often emerge where the physical evidence is thinnest, filling gaps in our understanding with extraordinary possibilities. One of the most persistent is the concept of acoustic levitation, the idea that specific sound frequencies could somehow negate gravity, allowing massive stones to float into place. Ancient legends from various cultures, including some Tibetan and Egyptian texts, speak of priests using chants, trumpets, or tuned stones to make objects weightless. Proponents point to the sheer precision of certain stone fittings, like those in Inca walls, and ask if such perfection could be achieved solely with brute force and copper tools. Could sound, carefully harnessed, have been a forgotten form of precision engineering? Another family of theories focuses on organic chemistry, on plant-based substances that might have acted as super lubricants or even temporary stone softeners. The idea suggests that ancient builders discovered a paste or liquid derived from local plants that dramatically reduced friction beyond what water or clay could achieve. Some even speculate about mixtures that could chemically soften the surface of granite or limestone, making it malleable for a short time, allowing for easier shaping and fitting before the stone rehardened. Then there are the complex wooden machines, the great cranes, winches, and frameworks that logic says must have existed but which left no trace in the archaeological record, having long since rotted away. Could they have been far more sophisticated than the simple sledges and levers we typically reconstruct? The absence of evidence here is not evidence of absence. Wood simply does not survive millennia in most climates. So we are left to imagine possibilities, grand assemblages of timber and rope that acted as ancient cranes, capable of feats we attribute only to modern steel. How do we weigh these captivating ideas against the established narrative of ramps and ropes? A useful guide is the principle known as Occam's razor. This is not a law but a rule of thumb in reasoning which states that among competing explanations, the one requiring the fewest new assumptions is often preferable. When we apply this lens, the sound levitation theory, while fascinating, requires us to accept an entirely new branch of physics for which we have no material evidence, no working models, and no clear mechanism described in any technical manual from the ancient world. The plant-based lubricant or softener theory is more plausible as it builds on known chemical principles. Yet even here we lack direct evidence. No residue analysis from quarry tools or transport roads has conclusively identified such a substance. The simplest sufficient explanation, supported by tomb paintings, quarry marks, experimental archaeology, and the sheer volume of manpower these societies could mobilize, remains the coordinated use of known simple machines, immense human labor, and brilliant seasonal planning. This does not make the lost technology theories meaningless. They serve a vital purpose, pushing us to look harder at the evidence we do have. They remind us that our understanding of the past is always incomplete, and that the absence of a wooden machine in the archaeological record does not prove it never existed. They challenge us to keep questioning, to avoid becoming too comfortable with a single story. The true lesson may lie in balance, holding the solid ground of evidence while allowing our curiosity to explore the shadows at the edge of the map. For now, the most powerful technology we can verify is not a secret chant or a magical plant, but the breathtaking ability of organized human communities to achieve the seemingly impossible with the tools they left plainly behind. Every pull of a rope demanded a tree. The silent machinery of ancient logistics, the sledges, the rollers, the barges, and the ramps, was built not just from stone and sweat, but from vast quantities of wood. This created a hidden environmental cost, a footprint left not in the soil, but in the disappearance of entire forests. To move a mountain, you often had to level a woodland first. The scale of this consumption is difficult to overstate. For the Great Pyramid alone, consider the wooden sledges needed for millions of blocks, the countless rollers placed and retrieved beneath them, the scaffolding for shaping stones, and the barges for river transport. Each element was a one-time use item consumed by the process. A single journey for a 50-ton stone might require a portable road of logs built just inches ahead of it, a disposable track of timber that was used once and then discarded or repurposed as fuel. This was an economy of attrition where forests were a strategic resource as critical as the quarries themselves. We see this pressure reflected in history and archaeology. The famed cedars of Lebanon, towering and rot-resistant, were prized across the ancient Near East. Egyptian texts boast of pharaohs sending great expeditions to Lebanon specifically to procure this lumber for building sacred barges to carry obelisks and for constructing large seagoing vessels. The demand was so intense that over centuries, these once vast cedar forests were pushed to the brink, their range shrinking dramatically due to this systematic harvesting for grand projects and shipbuilding. The impact was not confined to the desert kingdoms. In Neolithic Britain, the construction of Stonehenge and other henges required immense timbers for rollers, levers, and possibly for giant sledges or frameworks. Pollen samples taken from ancient soil layers around the Salisbury Plain show a marked decline in tree pollen, particularly oak and elm, during the periods of most intense monument building. This suggests that local woodlands were being cleared, not just for farmland as previously thought, but to supply the very tools of construction. This environmental pressure may have been a hidden engine for innovation. As local timber supplies dwindled, the cost and difficulty of overland hauling would have increased dramatically. This could have driven a pivotal shift in strategy, making river or coastal transport not just an option but a necessity. Why struggle to find enough trees for rollers to drag a stone 50 miles overland when you could build one sturdy raft and float it 100 miles with the current? Resource depletion might have forced a leap in efficiency, pushing cultures to master waterborne transport simply because the land route became too ecologically expensive. In some cases, the exhaustion of local forests could have even dictated the end of an era. A society might have built its greatest monuments in a burst of activity that consumed its available timber, and without that essential logistical resource, the ability to undertake further projects on that scale could have vanished for generations until the forest slowly recovered. The stones stand as a testament to human ambition, but the missing forests tell a parallel story of cost. They remind us that these ancient systems did not operate in a vacuum, but within a living, breathing environment that was both a tool and a limit. The legacy of a pyramid is visible for millennia, but the shadow of the forest that helped build it is a quieter, more sobering kind of monument. The silent demands of the supply chain did more than just deliver stone. They whispered directly into the architect's ear. The grand vision for a temple or a tomb was never conceived in a vacuum. It was born into a world of very real physical constraints. The type of stone available, the maximum size a barge could carry, and the sheer difficulty of positioning a multi-ton block hundreds of feet in the air. These were not mere inconveniences. They were fundamental design parameters, shaping the very form and function of the ancient world's most iconic structures. This is where logistics ceased to be a background service and became a co-author of architectural history. Consider the evolution of stone use itself. In the early dynastic period of Egypt, when the state's organizational power was at its peak and perhaps local timber was still abundant, we see the audacious use of colossal monoliths. The giant granite beams in the king's chamber, weighing 80 tons each, represent a peak of what the logistical system could deliver, a statement of absolute capability. But such feats were incredibly risky and resource-intensive. As time passed, even for the mighty Egyptians, a shift becomes visible. In later pyramids and temples, while still monumental, there is a noticeable trend toward more manageable stone sizes. The use of smaller, more regularly shaped blocks reduced the burden on every link of the chain, from quarrying to transport to final placement. This was not a decline in skill, but an optimization for sustainability, a design adapting to the long-term realities of its own supply network. This principle of adaptation for efficiency reaches its logical conclusion with the Romans. Their empire was built on speed, replication, and scale. The Roman answer to the megalithic headache was modularity. Their signature building technique, opus quadratum, used standardized rectangular blocks of consistent dimensions. Think of it like ancient Lego bricks. A block quarried in Tivoli could be shipped to Gaul, and a block from a quarry in Spain could be sent to Syria, and they would all fit together because they followed the same imperial template. This modular design was a direct gift from the logistics department. Standardized units were predictable to load, stable to ship, and fast to assemble by any trained legionary or local crew. It allowed the Romans to prefabricate elements at the quarry, shipping partially finished columns and capitals, and then rapidly assemble grand structures in newly conquered territories. The design of the building was literally dictated by what could be efficiently produced and shipped across thousands of miles of road and sea. Sometimes the adaptation is written not in the size of the stone, but in its very shape. Look at the central mystery of Stonehenge, the trilithon. This is the iconic form of two massive vertical sarsen stones capped by a horizontal lintel. Why this specific H shape? The logistical challenges of the Salisbury Plain offer a compelling answer. Erecting a single 50-ton stone upright is a monumental task of digging, levering, and packing. But placing a 20-ton lintel precisely on top of two such stones is a problem of a different order. The design of the trilithon itself may have been a brilliant logistical solution. The vertical stones could be erected first and stabilized. The lintel stones were likely shaped with protruding tenons or knobs on their underside. The uprights were carved with matching sockets or hollows on their tops. This meant that to place the lintel, the hauling crew did not need to perform a miracle of perfect balance. They only needed to raise the lintel to the correct height and then slide it horizontally until the tenons dropped into the sockets, locking the entire structure together with gravity and geometry. The iconic form is not just symbolic, it is profoundly practical, a design born from the acute understanding of what is possible when moving mountains with Neolithic technology. Even the choice of material often bowed to the map. A civilization might crave a specific, beautiful stone from a distant quarry, but if the journey was too perilous, a local substitute was found. The gleaming white marble of Carrara defined Roman imperial architecture, but for projects in the far eastern provinces, architects often used local limestone faced with stucco to mimic the prized marble's appearance. The design aesthetic was preserved, but the material was swapped for one the local supply chain could reliably provide. This is the hidden dialogue between ambition and reality. The dream of a building is filtered through the sieve of practicality. How far can the stone travel? How many people will it take to lift it? How long will the journey consume? The final structure we admire is always a compromise, a beautiful negotiation between the architect's vision and the logistician's sobering spreadsheet. The silent stones, in their very arrangement, tell the story of the roads and rivers that brought them home. For all the physical evidence, the most direct window into the ancient mind comes from marks they made not on stone, but on clay and papyrus. These are the written records, the administrative texts and inscriptions that capture the supply system not as we interpret it, but as they managed it in real time. This is the bureaucracy speaking, leaving a paper trail of orders, tallies, and complaints that turns our theories into documented fact. In Egypt, the tomb walls of nobles often served as a resume of their life's work. One famous scene from the tomb of Jehutifotep shows the transport of a colossal alabaster statue, estimated to weigh about 60 tons. We see the statue tied to a sledge, pulled by a team of 172 men in 4 rows. A foreman stands on the statue's knees, clapping his hands to set the rhythm. Most tellingly, a figure at the front pours liquid from a jar onto the ground. Precisely the act experimental archaeologists later proved was a practical lubricant, not a ritual. This is not an artist's imagination. It is a technical diagram, a visual manual for moving mountains commissioned by the official who oversaw the operation. It is logistics captured in art. Far earlier in the city-states of ancient Sumer, the world's first bureaucrats were obsessive record keepers. They pressed cuneiform script into soft clay tablets, creating receipts, inventories, and payrolls. We have tablets that meticulously list the daily barley and oil rations issued to workers, categorized by their job from the governor to the apprentice. One tablet might record the number of stones delivered from a quarry in a month, while another details the amount of fish distributed to the hauling crews. These are the spreadsheets of the 3rd millennium before the Common Era, proving that feeding and organizing a massive workforce was a calculated, data-driven operation long before the pyramids rose. The Romans, masters of system, embedded logistics into their legal framework. The famous Corpus Juris Civilis, the body of Roman law, included specific statutes governing the rights and responsibilities of quarry operators, ship captains carrying marble, and the builders who hired them. There were laws about who was liable if a stone broke during loading, contracts specifying delivery timelines to avoid delaying a temple's construction, and edicts regulating the use of the Imperial transport service for state projects. This legal codification turned logistics from an ad hoc effort into a regulated industry, where disputes could be settled in court based on written agreements. These texts do more than confirm our guesses, they reveal the human texture of the system. A Sumerian tablet might note an absentee worker deducting his ration. An Egyptian papyrus could record a complaint from a quarry foreman about a shortage of tools. A Roman contract might include a penalty clause for late delivery, showing that project managers then faced the same pressures as today. This written record transforms the anonymous masses into individuals with roles, rations, and responsibilities. It shows us that the true monument was not just the silent stone, but this humming, meticulous, and often frustrating business of coordination, captured in the fragile marks of ink and clay that survived the centuries. The grandest theories must eventually touch the earth, and for the ancient logistics systems, the ground itself holds the proof. Scattered across forgotten quarries and buried beneath desert sands are the physical fingerprints of the supply chain, the tangible evidence that turns our reconstructions from educated guesses into documented history. These are the archaeological smoking guns, the silent witnesses to the monumental effort of moving mountains. Start at the source in the quarries. The marks left by the quarrymen are not random scratches, they are a language of force and technique. At sites like Mons Claudianus in Egypt's eastern desert, the granite faces are pockmarked with thousands of small, circular depressions. These are the drill holes from the stone pounders, the relentless hammering of dolerite tools that slowly, grain by grain, liberated the prized granite for Rome's columns and statues. The spacing and depth of these holes reveal a systematic process, a grid of planned fracture lines. Nearby, you can find the deeper, wedge-shaped slots where iron or wooden wedges were driven to split the stone along those lines. The very shape of the quarry itself is evidence, a negative space carved with terraces and ramps that show how workers accessed the rock face and how they moved the freed blocks down to the transport area. These are not natural formations, they are the first chapter of the journey permanently etched into the landscape. But the quarry is only the beginning. To see the journey in motion, we must look for the roads. At Gebel el-Asr, the source of the gneiss stone used for royal statues and sarcophagi, archaeologists have found something extraordinary: actual sledge tracks. Cut into the bedrock leading from the quarry are parallel grooves, worn smooth over centuries of use by the wooden runners of heavy sledges. The spacing of these grooves matches the likely width of the sledges depicted in tomb paintings. They are not deep, but their very existence is a revelation. They show the exact paths the hauling crews took, the precise routes that became highways through the barren landscape, polished by the passage of countless tons of stone. These tracks are a moment frozen in stone, the literal path of least resistance chosen by generations of engineers. Further along the supply line, we sometimes find the tools of transport abandoned in place. In the marshes of northern Europe, near the sites of Neolithic timber circles that rivaled Stonehenge, archaeologists have discovered massive, preserved wooden rollers left in the boggy ground. These logs, sometimes over 10 feet long, were likely placed to create a stable track across soft earth and then left behind when the work was done. They are a snapshot of a logistical moment, a temporary roadway discarded after serving its single, vital purpose. Similarly, at the base of some ancient ramps and near loading areas, caches of worn rope fragments, broken levers, and even the remains of wooden sledges have been found. the discarded or lost equipment of the daily grind. Perhaps the most definitive evidence of a planned logistics network comes from the water's edge. At the pyramid complex of Giza, recent excavations have uncovered the remains of a massive, purpose-built harbor. This was not a simple riverbank, but a monumental basin dug into the limestone plateau, connected by a canal to a branch of the Nile. Its stone wharves and anchor points show it was designed to receive the heavy barges laden with granite from Aswan and limestone from Tura. At the Minoan Palace of Knossos on Crete, archaeologists have identified a sophisticated system of paved roads leading from the coast to the palace, roads wide enough and strong enough for the transport of large building materials. And at the Roman port of Ostia, the stone-loading piers with their pivot holes for giant cranes still stand, a permanent industrial installation dedicated to the business of moving stone. These harbors and docks are the undeniable hubs of the network. They represent a colossal investment of labor not for the final monument, but for the system that fed it. They prove that the builders knew the most critical part of the project was not the sacred chamber at the top, but the mundane, muddy port at the bottom. Each groove in the rock, each abandoned roller, each stone quay is a direct message from the past. They tell us without words that the grand vision was always rooted in the practical, that the path of the stone was as important as its final resting place. These physical traces are the forgotten signatures on the blueprint of history, the hard evidence that the silent ballet of logistics was very, very real. The final monument stands as a testament to the vision, but the true masterpiece was dismantled the moment the last stone was set. We have spent our time studying the visible, enduring artifact, but the real marvel was the temporary, invisible architecture that created it. This was the logistics network itself, a sprawling, dynamic system of quarries, roads, ramps, and barges, all coordinated by a living web of human planning. It was an achievement equal to the pyramid or the temple it served, yet it was designed to vanish. Once the final blocks slid into place, the purpose-built ramps were torn down, the wooden sledges and rollers were repurposed or rotted away, the seasonal workforce returned to their fields, and the administrative scrolls were filed away in dusty archives. The system consumed itself in the act of creation, leaving behind only the product of its labor as a silent, solitary clue. This is the profound irony of ancient megaprojects. We gaze in awe at the stone, but we are looking at the skeleton, not the living body. The vibrant, humming organism that conceived it, nourished it, and assembled it dissolved back into the landscape, its work complete. The paved roads to the quarries were reclaimed by the desert, the harbor basins silted up, and the precise knowledge of the foreman faded from memory. What remains is a magnificent fossil, pointing to a creature far more complex than its bones suggest. This invisible architecture was arguably a greater feat of engineering than the static monument it produced. Building a pyramid is a problem of mass and geometry. Building the system that builds the pyramid is a problem of time, distance, sustenance, and human coordination on a staggering scale. It required predicting the Nile flood years in advance, stockpiling grain to feed thousands, maintaining a fleet of barges, and training a rotating cadre of skilled workers, all while adapting to cracked obelisks, shifting weather, and the sheer unpredictability of moving mountains. The network had to be resilient, flexible, and self-correcting, a living entity that could learn from a failed transport and improve the next one. Its success was measured not in height, but in flow, the uninterrupted movement of material from a mountain in Aswan to a specific point in the sky over Giza. And when that flow ceased, the system had no reason to exist. It was the ultimate disposable tool, a single-use masterpiece of social and mechanical engineering. So when we stand before these ancient wonders, we are not just seeing a tomb or a temple. We are witnessing the final, frozen echo of a symphony. The stones are the lasting chord, but the music itself, the complex arrangement of countless moving parts working in perfect temporary harmony, has long since faded into silence. The true genius lies not in what endured, but in what was brilliantly, efficiently, and completely dismantled, leaving only its magnificent shadow cast in stone. That silent, vanished system is the ultimate lesson. For generations, we have marveled at the ancient world's engineering and artistry, the perfect angles and soaring heights. But the deeper truth is that these stone wonders are just the final, frozen artifacts of a far greater achievement. They are the byproduct of a triumph in logistics, a victory in organization. Before a single block could be carved with precision, it had to be moved with purpose, and that movement required a symphony of foresight, coordination, and communal effort that stretched across decades and hundreds of miles. The real innovation was not in the chisel, but in the schedule, not in the lever, but in the ledger that tracked its use. These projects reveal societies with a breathtaking capacity for long-term planning, thinking in scales of time that span generations. A pharaoh would order a pyramid, knowing he would never see it finished, trusting his administrators and their children to execute a plan that would outlive them all. This required a stable social contract, a cohesion strong enough to convince thousands of individuals to contribute their labor season after season, not for immediate reward, but for a shared legacy that would touch the sky. It shows us cultures that could see a landscape not as a set of obstacles, but as a toolkit reading the river's flood, the forest's timber, and the quarry's stone as interconnected parts of a single, solvable equation. So the next time you see an image of a pyramid, a stone circle, or a colossal statue, try to look past the silent geometry. See instead the bustling port, the chants of the hauling crews, the engineers surveying the ramp, and the scribes tallying the day's rations. See the dynamic, human-powered machine, the living network that was the true wonder, humming just long enough to leave a mountain in its wake. That invisible architecture of coordination is the most enduring monument of all, for it is written not in stone, but in the very fact that the stone is there.